Welcome to the sheet 2 energy conversion. In this sheet we are going to study about the basic problems related to the inductive energy storage, and in this video we are going to solve 4 problems related to the energy storing magnetic stored energy in a magnetic circuit. To start with, we are having an inductor with an inductance by experimentally to be of the form L is equal to 2L0 divided by 1 plus X by X0, where L0 is equal to 30 millihenries, X0 is equal to 0.87 mm, and X is the displacement of the movable element. The given winding resistance is of 110 milli ohms. We are having two different conditions. In condition 1, the displacement X is held at constant 0.9 mm and the current is increased from 0 to 6 amperes. Find the resultant magnetic stored energy in the inductor. We need to evaluate the resultant magnetic stored energy. And the second part is this X value has been changed from 0.9 to 1.8 mm and the current is kept constant at 6. Again we need to calculate the corresponding change in energy from this point to this point. What is the changing energy? It means what? We need to identify the energy at this point, and then the difference of energy stored at this point and the energy stored in this point will give the change in energy. To start with the solution, the calculated inductance of the experiment of the circuit, inductance L is given by 2L0 by 1 plus X divided by X0. It is given in the problem, this value. It is given in the problem. Well, L0 is equal to 30 millihenries, X0 is equal to 0.87, and X is changing from 0.9 first time. Initially it is changed to 0.9. Again this X is changed to 1.8. Now L0 initial conduct, initially it is given in the problem. X0 is equal to 0.87 mm given in the problem. X is the displacement. For X is equal to 0.9 mm, given current is 6 amperes. It is changed from 0 to 6 amperes. So the current flowing in the circuit is 6 amperes. Now what we need to evaluate? We need to evaluate the energy stored. Energy stored is given by half Li square, half into inductance value into the current square value. First let us calculate the inductance. Inductance L is equal to 2, from which just we are taking this formula, substitute in this 2 into L0 divided by 1 plus X by X0. X value is 0.9 mm and X0 is already given 0.87. 0.87 and 0.9 both are in millimeters, so into 10 power minus 3 into 10 power minus 3 will cancel out. You will get 0.9 by 0.87. Finally you will get 29.5 millihenries. This is the inductance of the circuit at a distance of 0.9 mm. But what we want the energy storage. Energy stored is equal to half into Li square. Taking this inductance, substitute the value half into L into I square. Current is 6, so you will get 0.531 joules. Next we are having the distance X is changed from 0.9 mm to 1.8 mm. So the inductance value will change. Why? Because inductance is depending on the X value as per the given information. This inductance is depending on the X value. So the new inductance value is 2 into L0 divided by 1 plus X by X0. X has been changed. So it will be 19.6 millihenries. 19.6 millihenries. It is 1.8 milli. Yeah, it's right. Now similarly, what we want? The change. We want the change in energy. What is the change in energy? It is energy during the second instant minus energy during the first instant. It means we need to calculate the energy during the first instant. So energy during the first instant means, second instant means omega is equal to half L I square, half into L value into I square. You will get some value, omega is equal to 0.353 joules. But change in energy is equal to W2 energy 2 minus energy 1. Difference of these two, you will get 0.178 joules. We are getting the negative value. Negative value means the energy has been lost. Energy storage has been lost. This much energy has been lost. Coming to the second problem, we are repeating the same problem number 1. Repeat problem 1. Assuming that the inductor is connected to a voltage source which increases from 0 to 0.4. It means the voltage value has been changed from 0 to 0.4. For the same circuit, the voltage value has been changed and held constant to 0.4 volts. We need to calculate both the calculations. It means previously the electrical parameter was from 6 amperes and it was held constant. Now the voltage has been changed. When the voltage has been changed, the current value will also change. Where is the current flowing? Current flowing in this resistance. Okay. Now let us repeat the same problem. It means at this distance, what is the energy stored? At this distance of 1.8 mm, what is the energy stored? And also the corresponding change in energy we need to evaluate. To solve this, given voltage is 0.4 volts, resistance is 110 milliohms, so the current flowing will be V by R. Voltage value divided by resistance, we will get 3.7 amperes. Previously the current was 6 amperes, so now the current is 3.7 amperes. If inductance is equal to 29.5 millihenries, this is given by at a distance of 30 mm. We are repeating the same thing but a different value of current. Now the inductance will be what? Same, it doesn't change. Why? We are calculating inductance is depending on the x value. We are calculating at the same distance, only the change is the current value. This inductance at a distance of x is equal to 0.9 mm, at a distance of 0.9 mm, inductance L is equal to 29.5 millihenries. So energy will be half L I square, half into L value into I square, current value 3.7 square. We are getting energy is equal to 0.202 joules. Now change the distance. We are changing the distance to 1.8 mm. X value has been changed and the inductance at this point 1.8 mm is 19.6 millihenries. The distance is maintained same. When the distance is maintained same, inductance value for this experimental setup is same. Now let us evaluate the energy. Energy is equal to half into L I square, half into L constant value into I square. Current has been changed from 6 amperes to 3.7 amperes. This is the 3.7 square. When you evaluate this, you will get energy is equal to 0.134 joules. Delta W is equal to 0.134 W2 minus W1. W2 value is 0.134 and W2 is 0.202. This energy you will get minus 0.068 joules. With this we have finished problem number 2. Let us go to problem number 3. Now the inductor of problem 2.1, sorry, it is same, the same one, the inductor, the same problem is driven by sinusoidal current source of the form I of t is equal to I naught sine omega t, where I naught is 5.5 amperes and the omega value, this omega value, angular frequency, angular speed is equal to omega is equal to 100 pi 2 pi f or 50 hertz, with the displacement held fixed constant at x is equal to x naught. Now the distance, this x is equal to x naught, x is equal to x naught. If the distance is held at this point, we need to calculate the time average magnetic stored energy. We need to calculate the time average magnetic stored energy in the inductor and also the time average power dissipated in the winding resistance. If we go to the solution, the given I of t is equal to I naught sine omega t. I naught is equal to 5.5 ampere. This is the maximum current, and omega is equal to 100 by 50 hertz. It is given in the problem, and also x is equal to x naught. What is x value? X is equal to x naught. X naught is given. It is given as, if we go to the problem, x naught is given as 0.87 mm, and x is equal to x naught. If we substitute x is equal to, let us calculate the RMS value first, RMS value of the current. If x is equal to x naught, if we substitute x is equal to x naught in this equation, if we substitute x is equal to x naught in this equation, we will get L is equal to L naught. See, x by x naught, 1 will cancel, so 1 plus 1 will get it as 2. 2 L naught divided by 2, you will get it as L naught. It means L is equal to L naught, which is equal to 30 millihenries. So we can write it as, when x is equal to x naught, L is equal to L naught, which is equal to 30 millihenries. Then RMS current I is equal to maximum value divided by root 2. Maximum value is equal to 5.5. 5.5 divided by root 2 is equal to 3.89 amperes. And omega is equal to half Li square. Energy stored is equal to half Li square. Substitute the value of L, which we got it from here, into I square is current RMS value is 3.89 square. You will get W is equal to 0.227 joules. So power dissipated is equal to I square R. Power dissipated. The question asked is, you need to understand the question. He's saying that power dissipated in the winding resistance, or simply if he says power dissipated also, we need to evaluate the power dissipated. Where it is dissipated wherever we are having the resistance, and resistance is available in the winding. So simply we can say it as, we can take the resistance of the winding. So power dissipated is equal to I square R. I square RMS value is equal to 3.89 the whole square into R value is 0.11, which is 110 milliohms. So we will write it as 0.11. On calculation, you will get power dissipated is equal to 1.664 watts. This is the power dissipated. Coming to the problem number 4. Problem number 4, we are having an actuator with a rotating vane. Assume that permeability of both the core and the vane are infinite. Assume the permeability of the core and vane are infinity. It means the reluctance is 0 for the core and the vane. The total air gap length is 2g, and the shape of the vane is such that the effective area of the air gap, if you see this is the circuit, this is the core we are having, this is the vane, and this is the pivot holding the vane. Permeability of this core and the permeability of this vane is infinite. So the reluctance value of this and this will be 0. Only the reluctance is available at the air gap. So the reluctance is available at the air gap. Next, what we need to evaluate, if you see the question, assume he has given the dimensions of the air gap, cross-sectional area, and the number of turns 650, and air gap effective cross-sectional area is Ag is equal to A naught into 1 minus 4t by pi the whole square. What we need to calculate, assume the coil current to be I is the current flowing in the coil. We need to identify the expression for the magnetic stored energy in the actuator as a function of theta less than pi by 6, and also the corresponding inductance value. This is the thing we need to evaluate. So what we know F is equal to Ni is equal to HL, sheet 1. These formulas are from sheet 1, and also flux density is equal to mu naught H. So H is equal to B by mu naught, and length of the air gap is equal to 2g. Length of the air gap, see the question, one g is here, other g is here, so the air gap width is equal to 2g. And flux density, we can write it as n, in place of h we can write b by mu naught, so b is equal to mu naught ni by L. So flux density in the air gap is equal to mu naught ni by 2g. Energy stored will be equal to flux density square into volume of the air gap. This is the new formula. Energy, if you check the nursery, you will find this Bg square, flux density is equal to energy stored is equal to flux density square divided by say simply mu naught. What we want? We want Bg. Sorry, we want energy storage. Energy storage is equal to Bg square by 2 mu naught into Vg. In place of Bg, we will substitute this mu naught ni by 2g. Mu naught ni by 2g, and if you cancel, you will get it as mu naught, one mu naught from here and mu naught from here will get cancelled. You will get mu naught n square I square by 2g square. It means 4g square. You will get 4g square into 2 mu naught and also this volume can be written as, this is the volume of the air gap. Volume can be written as length of the air gap into cross sectional area of the air gap. Length of the air gap is 2g, so 2g into cross sectional area of the air gap. On simplification, finally you will get it as mu naught n square I square by 4g into ag. But we know the cross sectional area of the air gap, it is given as, if you go to the problem, we are having ag is equal to a naught into 1 minus 4t by pi the whole square. Just we are substituting this in this area, you will get this is the expression of the energy stored in the field. Now after substituting this, you will get energy stored in the field. Coming to the B part, the next parameter is we need to evaluate the inductance. Inductance is given by half L I square. We know energy stored is equal to half L I square. We need to calculate L. So L is equal to 2 omega field divided by I square. 2 from this side and I square down. You will get 2 omega field by I square. Just substitute the values. Of energy of the field. What we got it as this complete expression. Just place it here, divided by I square. So I square gets cancelled. Finally you will get it as 2 into mu naught n square by g. This 2 value and 2 will get cancelled. 2 and 4 will get cancelled, as remaining will be 2. G will be as it is. I square gets cancelled, and remaining terms, only the terms which are getting removed are I square and 2 from here. So the remaining parameter will be for inductance. So L is equal to mu naught n square by 2g a naught into 1 minus 4 by 4 theta by pi the whole square. The same problem can be extended by giving the values of theta. This problem can be extended. Say the theta value is 20 degrees. If we are considering theta is equal to 20, then we need to substitute theta in radians. In radians, if you need to substitute, the g value will be given, cross sectional area will be given, number of turns will be given, and we need to calculate the inductance. With this, we have finished 4 problems related to the energy storage in magnetic circuit, and the remaining problems will be discussed in the next session, where we are having multiple coils. Here these first 4 problems are related to the single coil energy storage problems. With this I conclude. Let us stop it here. In the next video you will see problems related to the multiple coils.